Africa, and that's my email address, mayu.fict@isbatuniversity.com. So you can reach out to me after this if it's required any kind of a collaboration, or either you're already working on the electronic chips, or you're already working on the photonic integrated circuits, photonic crystal, band gap structures, optical fibers, passive devices. If you're already optical communications, so if you're already on this domain, then definitely we can do a kind of collaborative research works, and definitely we shall see that how we can go ahead with good collaborations as well, right? So with this, today I'll be talking about more about to the photonic crystals, the band gap structures, and how we have working on this photonic chips, and definitely how they are going to solve the theme of this FDP, which is all about the next generation technologies actually, and that is all about the research which we are doing at ISBAT University, which is already on my continuing work of my the PhD research works. And since some of my faculty is already working on the electronic side, so let's see how we can work from electronics, which we call them as EICs, electronic integrated chips, to the PICs, which is we call as the photonic integrated chips. So why we need to transfer from electronics to photonics? What is the need of it? Let's discuss in a few more time, and then I hope it will be a fruitful discussion. And after that, if you have any queries in between, also even at the end, please reach out to me, or even we can discuss here on this platform actually. So for the today's talk, we'll be talking about to the integrated circuits, and that's what we'll be talking about now, to the electronic ICs, more made up of the transistors or the semiconductor devices, and what is their limit now, which is going to be as per the Moore's law. And then further we shall be discussing about the photonic integrated circuits, then how this integrated circuit can be designed using the photonic crystals. We also know them as the band gap structures. In that, what we have done work recently on the band gap structures made up of the passive components like the filters, multiplexer, demultiplexer, even to the optical switches, optical encoders. So we have a wide variety of optical passive devices, which we usually study as a part of digital electronics, as a part of electronic devices, solid state devices, microprocessor, VLSI. So we already discussed all this part as a part of electronics, but how they can be designed using on the platform, which is what called as a system on chip, SoC, using the photonic crystals, that we shall be discussing, and also how we have designed those photonic integrated circuits, and what is their future perspective also. And lastly, what research activities and research, not only about the electronics, also to the photonics, what activities we are doing at ISBAT University, also we shall be discussing here, and maybe that will be concluding the today's FDP talk actually. So let's talk about now to the what we already have, which we call as the integrated circuits now. And we, as all our faculty members, I believe some of you must be from the electronics background. Even though you are from computer engineering, even though you are from computer science, this talk is going to be very important, because the future generations, we are looking forward for everyone is looking for the data actually. And when everyone is looking for the data, we are talking about more processing, the more the storage, and this is where we're going to have the limit on those number of transistors. And that's what you can see in one of my slides, which you can see here, that by 2036 we'll be having more like hundreds of trillion transistors on a single chip actually. And that's what you can see now. As of now, we have around 10 trillion transistors on a single chip. But where are the future is going to be going ahead? Since my the colleagues from the computer engineering or the computer science background must be talking about the data science, machine learning models, even to the AI now today. Everyone is talking about using those chat GPTs and the different other platforms for solving your day-to-day tasks. Either you are a researcher, or you're a scholar, or even you are a faculty member, either to generate a question bank, or to make nice slides, or whatever the ways you're using those platforms. But again, you see now, you are responsible to consuming a lot of data on daily basis now. And where this data is going to be stored, this is where the challenge we are finding in terms of the electronic circuitry, because there is a limitation to store those devices. How many transistors we are going to have on a single chip, and this is where the limitation is there. So when you look at for the electronic circuits, when you talk about the microchips, it came around somewhere around 1950s, and it becomes a very vital component of the today's electronic circuit. And you'll be surprised to know, after the invention of 1947 for those transistors, we're still using them. up to 2022, just we celebrated like 75th anniversary of the invention of transistors, right? And now we are still using those transistors. What do we have for the next generation technology? And this is what we have to think as a young engineers, young faculty members. I believe we are faculty of engineering, must be having some engineering degree or a physicist or all those backgrounds which we have as a part of study. We are talking about what is the next generation technology is going to be. It's based on the quantum photonics or the photonics integrated circuit, which is going to be the future of those integrated circuitry actually. So when you look at for the electronic integrated circuitry, it all started from those silicon transistor which was invented in 1947, and then it became for a wide variety of application for research, like you can see for making your DRAMs and different other chips for digital clocks, even to your mobile phone, personal computer, video game, even to the smartphones. Everywhere we're talking about those transistors actually, especially. And not only about the transistor, we also use those basic components like the capacitor, diodes, transistors, and all of them are the part of this. Now where are we going to go ahead? Now suppose we already have those millions of transistors. Now you say million transistors. Now we are having the billions of transistors. Now we are almost reached around the latest processor around 10 trillion transistors on a single chip. Now what is the future we are looking forward for? And that's what we say is as per the, it's not as a Moore's law, but the founder of Intel once said that every second year the number of transistors are getting double on a chip actually. So by this time we already have the 10 trillion, and then you can see on my screen now again we have 10 trillion transistors, but where the future is going to be going ahead, that is what we have to look for, an alternative solution technologies which can be smaller in size, which can be faster, and which can have more storage. All this could be possible using those photonic integrated circuits, and that is where we're talking about now to the photonic integrated circuit, which we call as the PICs now in the today's time, because the semiconductor for the photonic devices normally is made up of silicon. You can see moreover we talk about the electronics background, we have only the semiconductor silicon and the germanium, and silicon easy to available and abundant in the nature, and that's what we have the Silicon Valley and all those domains. But do we have other combination of materials? And this is what we have another advantage of having the photonic integrated circuits, where we can also have another group of materials which is called as your combination from group 3 and group 5. Now we have like the indium phosphide, gallium arsenide, gallium indium phosphide, gallium indium phosphide arsenide. So we have a wide silicon carbide. So now we have a wide variety of you can say as a group of a different combination of materials which we can have from this materials actually, which all are the directed materials which we shall be discussing on next few more minutes. So when you look at for this PICs, it usually came during 1970s, and it's an optical equivalent of those electronic ICs, and that's what we're talking about now, from EICs to the PICs actually. It involves the integration of optical functions onto a single chip, high speed data rates, and that's what we are going to show you one of the paper which we had around terahertz, and then it's a small size and reduced power consumption, and that's what I was talking about. This FDP talk is not only about from electronics and communication engineers. Even though you're from electrical background, you're talking about power and energy, and you're talking about now net zero consumption. But how are we going to achieve that? Using those electronic circuitry, because either you're from electrical background, you're talking about power and energy. If you're from data science or computer engineering, computer science, you're talking about a lot of data with the machine learning models, even a lot of big file size. How are we going to, and as a communication engineer, definitely you have to provide access to both of them actually. So how it is going to be even possible with those? The solution again is on the PICs for your data center. And one of the slides I will show you one of the recent this year actually, that ST Microelectronics, they implemented their photonics chips to their data centers actually, so that it can have the lesser the power consumption, because to make cool down those data centers again required a lot of huge air conditioning. It requires a lot of energy and power to maintain those data centers actually, right? So on the daily basis we are having a lot of data. How to cool down them? Again we're talking about those net zero, and this is where the PICs are playing important role, and this is where we're talking about the next generation technology as your the PICs, which you call as the photonic integrated circuits actually. And some of you may be familiar with this kind of chart, but those who are still new, look at this slide where we're talking about now to the historical perspective of those silicon photonics. Because why silicon have been playing every time an important role? Because yes, it's a semiconductor material and easy to available, and especially When you look at for the refractive index of silicon around 3.47 is very suitable for optical windows, and that's why most of the optical communication now we are trying to do with those silicon as a materials actually. So when you look at for this materials, we had those the transistors which came during earlier 1950s, and then after that if you see keep going on, a lot of technology development has happened over the period of time to this optics and photonics actually. And that's what you can see again. One of the things about during 2006 we had the Couture commercialized the first silicon photonic variable optical attenuators. So it's not about like we are not using them now. A lot of companies have already started developing those silicon photonics based products, like we had from Couture, then Luxtera, then we have Intel, then Rockwell Telecommunication, Tower Semiconductors. So these are the different organizations which are already in the development of silicon photonics. For a moment, Dr. Malika Rajun, you are saying something, sir? You raise your hand. Professor, you are saying something? Hello. Okay. So shall we
Nothing,
continue?
sir. Sir, you please proceed. You please
Okay.
continue, sir.
Sorry, I just saw the raised hand, so I thought maybe some professor is asking something. Okay. So now, when you look at for one of the like the CTO of the Effect Photonics, he says like the way we purchase our electronic component from our store. Like suppose you're doing a project and you says I need this kind of transistor, I need this kind of maybe a diode or a capacitor or transistor. Likewise, you'll be future you'll be going to the market and just there will be similar kind of data sheets which we have the different types of the optical components, and you'll just go and purchase from the shop actually. So this is what uh, the CTO says, that because the future is going to be about the photonic integrated circuits, where talking about the different photonic components you go and buy and just solder it to your circuit, and the design can work actually. So yes, this is where we're talking about now to the next generation technologies actually. So when you look at now to the PICs, let's see some more technical details now here. So these PICs are actually the advanced system on a chip, SoC is what we call it, enabling the transmission of data at high speeds using optical carriers within a spectrum of around from 350 nanometer to around 1650 nanometer, and it's covering all the three optical windows like 870 nanometer, 1310, 1550, 1440, and so all the wavelengths are getting covered by this PICs. Secondly, you can it's a highly scalable integration of multiple optical components on a single component chip from few micron size to millimeter size also. And the future integration with electronic circuitry, the driver, the logic gates will further expand the PIC functionality for wider market application. And this is where we can see now all those components which we study as a part of electronics can be designed using those of the photonics technology section. And when you look at for the common components of the PICs, it's all about the optical amplifier. So it's a combination of both. It's a combination of the active devices, we're talking about your amplifiers, the sources, and then to the detectors as well. And then you're talking about the passive components, where you're talking about your mux and demux, maybe to your optical waveguides, optical fiber, attenuators, the filter, the switches. These all are part of the passive components. And now this all PIC materials which are available now, as I said again, we have the SOI, silicon on insulator or a wafer. Then we have lithium bionate, we have a gallium arsenide, indium gallium arsenide phosphide, silicon nitride, indium phosphide, silica as a wafer actually. So yes, we do have a wide variety of applications to design those PICs, which we call it as a photonic integrated circuits actually. So when you look at for this integrated photonics, is actually a next generation disruptive technology critical to meeting the size, and this is where we're talking about in terms of comparison to the electronics. So those of my colleagues are from electronics background, they can understand we're talking about the size is very important. because the size of the transistor again going have reached already to the nanoscale and even now to the angstrom scale around, yeah, around 20 or 10 angstrom. That is what we have the size as of now for the transistor. But what is the future? How small size of the transistor we can go ahead actually, right? And the next is all about the weight, right? The transistors are actually a bit heavy in the size. Then to the power consumption is too much power consumption for those transistors. Now you think logically, like we are using those small smartphone with you, and you have a very transistor on that on a processor. How you eat it up very easily, right? And when you're talking about now to the data centers, which is having the, like, trillions of transistors on a single chip, and they have like the like some few thousands of processor on a single board. How much energy they are going to generate, and to cool down them again you need to have a lot of air conditioning, so that a lot of power is required to maintain those data centers actually, and as well as the performance goals for the many diverse applications. So the key benefits, which is all about for the PICs, and which any one of you or anyone of interested to design those integrated circuits can think for, as the PICs, the 50% less mass and the power, then 100 times size reduction, higher bandwidth and the data rates, no cost redundancy, aperture independent, so as you can integrate with both fiber and then to the devices, transparent to modulation format, versatile and scalable. And this is where we talk about to the photonic integrated circuit, which are offering improvements in performance and reliability of those integrated circuits. And this is what I was talking about now, the combination of active, passive, and then to the final it comes to the integration of them actually on a PICs, that is called as the large scale PICs and on chip interconnects. So you can see now in active devices we have like your lasers, then you have a photodetector, even you have a modulators. All those are the part of the active component. So if any of your faculty member interested to design that, also can start working on them. Secondly, you do have now this passive components, which can be using like your mux and demux, then couplers, then optical filters, optical switches, splitters, and even to the polarization diversity. So I think most of these components which we have already have been designed in the past few years, and now after that we have tried to integrate all of them on a single chip actually. And when you look at for the size of those PICs, it will look like less than to a grain size or the rice size what you have in your hand. But this is what the size of this PICs actually. So it occupies very less mass and the power, and also to the size is very small in comparison to those of electronic circuitry actually. So when you look at for further to this the application of this PICs, these chips are also faces pressure from the data surge in a big data IoT devices, and the today's time even to your AI, causing the bandwidth bottlenecks and the slower the data transfer speed. And that is what the solution we have is a photonic integrated circuit in comparison to your electronic integrated circuit. So this photonic integrated circuit, the PICs offers a transformative architecture using light signals instead of electrical signals. We are talking about light as a carrier there, and potentially addressing the growing data demands. And that's what we can see on a, now for an example here. Now here we have an optical fiber which is being joined with those devices. We have a photonic crystal switch over there. We do have the photodiodes, then we do have a ring resonators, we have a laser as a source over there, we have couplers to couple the light to the different waveguides, we have an optical modulator. So you can see all of them have been integrated on a single chip, and that's what we're talking about now to the PIC. That is what we call as the photonic integrated chips. So this is one of the view of those PICs, that how those ICs actually looks like actually. So another way which we have seen this PICs looks like, where we can see another the designing of this integrated circuitry in the nanoscale. This is what you can see it here, that we have a tapper which is being used to connect those fiber to the photonic crystal structures, and then it is being passing through the splitter. From splitter it is going to the demultiplexer, and from demultiplexer it is going to the different output ports depending on what is the need and particular wavelength of light has to be reached. And then we also have the cross connect. We also call it as optical switches. Instead of from one waveguide it can switch to the another waveguide. And then we have a waveguide curvature, and you'll be surprised to again know some of my colleagues who are already in teaching of optical fibers, and we study that when you bend an optical fiber at an angle of 90 degree, there is no TIR, the total internal reflection. But when you see in the sharp bands in the photonic crystal structure, even the successful transition can be made even at the 90-degree sharp band as well. So this is where this, you can say, the waveguide curvatures can be designed using those of the photonic crystal structures actually. And then lastly, we do have an optical resonator. So particular wavelength of light is going to be resonate from the structures, and others are going to be dropped from it. So this is what you can see actually. When you design the structure, it looks like this kind of a waveguide structure, but when it comes to design on the photonic crystal wafer, they actually looks like this kind of a structure, which you can see on my screen now actually. So this is what we're seeing from the taper.
Hello, Bora madam, whether speaker is there?
Yes, sir. Might be his connection got interrupted.
Huh?
Might be he will
Disconnected,
join again. Yeah. Just now he got disconnected. I will try to contact him, sir.
Yeah.
Might
Please,
be he.
please. Huh?
Yes, sir.
Okay.
Okay.
Okay, so just confirm to me if it's available again.
Yes, sir. Yeah,
Okay, please.
it's all right.
So this is what you can see now to the integrated circuitry for the photonic crystal structures. This is where you can see that because you'll be able to see when you're talking about the design of photonic crystal structures. Initially, when we started, I'm telling you something which I've done actually. So we used to design a single component, like we have designed an like a filter, we have designed like of a optical switch, then we have designed maybe a waveguide, then optical bands, then to the filters, then to a mux and demux, then how it all can be integrated on a single chip. And this is where we find a lot of challenges to design all of them on a single chip. This paper will help you out to understand that how those integrated circuitry of the PICs looks like actually. So when you look at for the structures now, we will be able to see that from the input side we have an optical uh, from we have an input port, and then we have different types of outputs you can see below here, and then you can see here we have like uh, so you can see here now, so from input port it's going to the rectangular waveguide, which we call as the Fourier crystal waveguide. From there it is passing through the beam splitter. From beam splitter it is again going to the optical cross current, which we can call as an optical switch. From there it is going to the 5B as a to the optical resonator. From resonator it is passing through the again to the optical bands. From bands it is again going to the phase shifter and passing through the wavelength multiplexer, and finally it is reaching to the output port B actually. So this is what you can say that how we are going to have an integration of many, you can say, as different components are going to be integrated on a single chip. Because when you look at for this kind of a structure, or even a broader way, when you look at for this kind of a structure, we always see in that way that this looks like as a different component, but how they all can be integrated, and this is where we're talking about a solution for a photonic integrated circuit. So usually you'll be able to see this kind of structure in the different papers, but how actually is each component is going to be looking like, this is how it is going to be on another design. But when you look at for each and individual design, this is how it is going to be incorporated on a single chip. So once you have all of them on a wafer, they all are going to be integrated together. You can have an entire integrated circuitry actually, from input to the input port to the output port. So when you look at for this structure, now here we're talking about the different structures, or you can say the different components which I'm showing it to you here. It's all are designing using those the photonic crystal based integrated circuitry. So what actually is all about to the photonic crystal? This is where I'm talking about to you that how this individual component or as well as the integrated circuitry can be designed using those the photonic crystal structure. We call them as the band gap structures. So what is all about the photonic crystal? What is the history of it? How it all started, and then some work which we have designed and which we are doing at present as well, and then we shall be seeing in a few minutes of time. So this is just was about to show you that what is all about to the from electronics ICs to the PICs, what is the need of it and how they really looks like, but how they can be designed. Now suppose some of my colleagues or faculty members want to say, Mayur, I also want to start all these things. How can I start my all? So let us see some introduction about the photonic crystals. Actually, the photonic crystals is actually is a periodic arrangement of a dielectric material that exhibit strong interaction with the light actually. So when you look at for these structures, they can be designed in one-dimensional, two-dimensional, and even to the three-dimensional as well. Now, what do you mean by the 1D, 2D, and 3D? Actually, one-dimensional, you can see it here on the structure that you can see there are the two color strips. One is green and one is the blue. So they are the two different materials repeating periodically. Now, I don't know if you can recall the structure of comb, which we usually for the comb our hairs. They have like comb teeth, and then there is a space. We can consider this as an air, right? Then a comb teeth, and then space, and air, then comb teeth and air, and comb teeth air. So this can be a periodic structure, and this is what we mostly use for the grating actually. So those of my colleagues already working on optical grating, that is actually 1D photonic crystals, which we are using for very many application for even sensing purpose as well. A lot of work people do a lot on a different combination of materials. They can have 1 and 2D, all those materials. They can have the different types of materials they can exhibit, and they can do a lot of research work on this domain. But my work especially is on based on the 2D photonic crystal, where you can see there is a repetition of materials, the two different directions, and 3D in again 3 directions. But you'll be surprised to know that the 1D was came around 1887, even before to that of the transistors. I'm going to show you one of the work that how the photonics came even before to the electronics, but people didn't find it in that way actually. And then during 1987, it came with the 2D and then the 3D photonic crystal structure, and these different colors exhibit the different, you can say the different types of dielectric materials actually. So when someone says 1887, how come the 1D photonic crystal came? And that's what I can show you one of the research paper. It was a very popular known scientist, Lord Rayleigh. In 1887, his paper was published with the Journal of Science, philosophical magazine as well, and it says that on the propagation of waves through a medium endowed with a periodic structure, and this is where the first time someone was talking about those the photonic crystal structures actually, because the periodic, because we just now talked about the definition of the photonic crystal says the periodic arrangement of dielectric material that exhibit the strong interaction with the light. This is where the first time in 1887 was stated by the Lord Rayleigh on his paper on the propagation of waves through a medium endowed with the periodic structure. So this is the first time someone was talking about those periodic structure, and after some 100 years of it, around 1987, the two scientists brought their papers. One is Ali Yabolovich, very popular name for photonics and photonic crystals, and second is the Sanjeev John, who brought their two papers with the physical, the PRLs, the physical review letters during the same. One was came in volume 58 around number 20 and 23, just around some May and June, few days of difference, but we came to know about like you can say about the 2D and then to the 3D photonic crystals actually. So this work introduced about the photonic band gaps, photonic crystals, the periodic structure, and this is where people find it that it's so useful to talk about now to the photonic crystal structures. But again the question comes, is it something like we talk about your the electronics now, when you compare from electronics to the photonics, and when you're bridging from electronics to the photonics, the electronics, the components are made up of actually the natural materials, right? Or we have the natural lattice structures. The atomic structure is the natural, which we get it from the nature, either from silicon or the germanium. But when you look at for this photonic crystal, the structures are actually the man-made. They are artificial structures. They are not natural structures. But this concept of photonic crystal, the word, the photonics, the photonic crystal about the band gap structure is not new. It comes from the nature. When you look at for the feather of a butterfly, the feather of a peacock or opal or the sea mouse or the wood boring beetle, when you look at their structure at the nanoscale, and you'll be able to see that they exhibit strong periodic structures. Now, what do you know the strong periodic structure that we can see on the right at the ABC structure? When you look at the feather of a peacock or a feather of a butterfly, they exhibit as a periodic structure. So whenever a particular wavelength of light interact with those band gap structure, they exhibit the different wavelength of light, and this is where the concept of the photonic crystal comes actually. And this is what actually the need of the photonic crystal. It comes to understand that how the different types of structures can be designed with those photonic crystal metals. Now, when you look at for designing of this component, as I told you, I've mostly worked on my 2D photonic crystal structures. On the 2D photonic crystal structures, we can have the two kinds of structures. One, either we can have it as a dielectric rods on a wafer. So I don't know, again, if I tell you the 1D photonic crystal, I just give an example of maybe your a teeth, the comb actually, which is the longer one, not a round one, right? So when you have a longer teeth, which we usually use at our home, it is a 1D photonic crystal, right? But I don't know, the recent trends, people use it, the comb, which is the round one actually. You see, it looks like as a round wafer. It may be a plastic wafer, yeah, obviously. And on that you have a teeth, and it's not only in one direction, they are actually in the two directions. And that's what you can see how we have the structure made up of like a rod on a wafer structure. So resembles, you can see with that comb which you can see. The second structure, either you can have rods on a wafer structure, or it can be holes on a dielectric slab. Now the dielectric slab, if you can understand, another example for this is a honeycomb. The honeycomb, you can see, looks like as the holes on a wafer structure. So these holes can also be created on a particular distance, maintaining the different shape and size, and that's what we can have either to the square lattice structure or we can have a triangular lattice structure, we can have a rectangular lattice structure. So we have the different types of lattice structure, that how those rods looks like actually. And once we are talking about those structures, we can have the strong exhibition of light, that how the light can propagate through those structures actually. So once we can have those structures, it's very easy to have those structures, it's very okay. But what are we talking about now? The photonic crystal, because since it is a dielectric material, and as you are aware, the properties of properties of those dielectric materials, which cannot allow the propagation of light actually. So what could be the possibility for that? The possibility to propagation of light, to create the defect. It means what? We are creating the defect to break the periodicity of those structures. Let me say it again. In such a way, in this periodic structure, since it's a perfect structure, like let me show you this another structure. This looks like as a perfect structure. If all the rods are made up of blue color, then they're perfect structure. There is no defect, no propagation of electromagnetic waves. The light signals cannot propagate through the structure. So to allow them to propagate through the structures, or I can say another way, the defect is equivalent to breaking the perfect periodicity of the crystal lattice. So to break the periodicity, we need to create the defects. Now these defects actually can be two ways. One can be a point defect, and another one can be a line defect. So the point defect means we are talking about a single rod now. The single rod, what is going to be happen in the single rod? Either you can uh, change the position, is another defect. Either you increase the radius of a particular rod, or you decrease it, you shift its position, or you just remove it from there. Is another different types of defects what we can understand. The same way, if it's being done only with the single rod, it is called as a point defect. But once it is being done for the a particular line of rods, then it is called as the line defect. Actually, that's what you can see another example with the red lines here. It's called as a line defect. So whenever we have to create maybe a waveguide where the particular wavelength of light can travel, we create it as a line defect. And whenever we have to create a resonator structures, that's what we've seen in the previous structure. We're talking about the ring resonators. So whenever you have to create a resonator structure, we try to create with using the point defect. Actually, this is very important to understand to create the defects, because the it can guide the light from one point to another without much losses, even around the bands with the radius of curvature comparable to the wavelength. So the defects in photonic crystal waveguides shows the frequency selective propagation and photocrystal waveguide. It means what? It's not about you can just create a defect. What wavelength of light? It has to be a frequency selective. You're talking about the GPON network, you're talking about the any other passive optical networks, any network you're talking about optical communication. We are talking about a particular wavelength of light actually. So once you know about what wavelength of light is going to propagate, the structure should also allow them to propagate on a particular wavelength of light. But how do we find what wavelength of light is going to be designed? Yes, that is what we can say about this photonic crystal waveguide structures are actually the frequency selective. This is, we have just discussed about the different types of the defects which we have is a point as a point defect and as a line defects. When you're talking about for a particular rod or the hole on a wafer, it can be both ways. It is a point defect, or it can be a line defect when you're talking about a particular waveguide to create a waveguide structure. But again, to create those ring resonator structures, especially, how we can create those ring resonator structures for photonic crystals. So for designing, now some of you, like some of us, my colleagues, may be already working on this photonics. It's not that easy to say like we create the structure and it is working. No, it's not that so easy. It has to be have a lot of physics behind it, and you have to do a lot many calculations sometimes when you have to design this. It's not just about like you have a simulation tool, you drag and drop here there and it says now it is done. It cannot work like that. So for designing those photonic crystal structures now, let us see what we have tried to design. First of all, what is the responsibility is all about the number of defects. Means how many defects either we're going to have either square or a rectangular structure, how many rods are there, how compact we want to have the structure. That is what is important. Secondly, the distance between the defects. What do you mean the distance? What we call as the lattice constant or the pitch. They are the different names and the different references, but the distance between the defects means after what is the periodicity is getting repeated. Like in a one direction of the comb, you have a comb teeth, then there is a space, and there is a comb teeth, right? So what is the space in between them? That is what we call as the lattice constant in these structures actually. Then the size of the defect means either talking about the radius or the the diameter of those holes or the radius of those roads is very, very important. And lastly, the refractive index of the materials, because either talking about silicon or the germanium, gallium, indium phosphide, gallium arsenide, indium phosphide, what combination of group 3 and group 5 you're going to use it, it should be accountable actually. So once you have design of the structure, you need to consider all those parameters actually. And some of my recently I come across one or two papers where people are talking about now to apply those machine learning models to get optimized parameter of those the structures, so that you can see that the defects can pass through those structures, and you can talk about now particular wavelength of light can travel with those structures. But as I said again, this structure exhibit a frequency selective, means what if I choose these parameters effectively, okay, what wavelength of light is going to propagate. So when you look at for the what we call as the photonic band gap, and especially when you search on This you can call them as a photonic crystal or the band gap structures. You need to talk about, like for an example, like silicon having a refractive index of 3.46 around, having a photonic band gap which is in the range of 1139 nanometer to 1846 nanometer. Now you'll be surprised to see now this material is of silicon with this refractive index exhibiting a strong photonic band gap in the range of this from around 1140 to around 1850 around. And this entire optical window which we are using for optical communication, everything is being followed by even to those of silicon actually. So this is what we can design those silicon, because usually for designing those optical fibers or using those sources, especially we don't choose for silicon. Why? Because silicon is an indirect band gap material, but detectors we can make it for the silicon, but here the structures also you can design using of those silicon as a material structure. And when you look at for this structures examples now, when you try to see like what kind of structure, just now we talked about like these structures can be used to create waveguides. A waveguide means where a particular wavelength of light is going to travel. Like you can say a third point here, the photonic crystal waveguide, where is a light defect is being created. Ring resonator where a point defect is being created. So let us try to create those defects and try to see that how those defects are responsible for it. Let us see in such a way that here this structure you can see now. So here you can see now here we have created you can say this waveguide structure where particular line can be a particular rods have been removed to create the line defect. And another way here you can say it as, you can say from here input to the output side, here this an L shape, or you can see at a 90-degree bend has been created so that a particular wavelength of light can pass through those structures actually. So when you look at further for now to the designing of this ring resonator structure, yes, we can either use this of your point defect or the line defect, or we can create those resonators using those ring shaped structures actually. So how this ring resonator structures can be designed, you can see it here now, especially from port 1 to the port 2, then port 3 and port 4. We have like 4 ports waveguide, or you can say we have the 2 waveguides. In between them we have connected to the ring resonator. Now what happens actually when you're talking about using optical fiber as the resonator structure, we can still use optical fiber. But what is happening when you band two optical fibers, again you join them end to end, and the losses in terms of the coupling losses and then to the waveguide losses are very high using optical fiber. So what could be the solution? We can have those structures using those of the photonic crystals now. So where particular wavelength of light is being inserted from port 1, it can go to the port 2 without affecting to the resonator, or the resonator has been designed in such a way so that particular wavelength of light is being coupled and is going to be dropped either to the forward transfer to the port 3, or it can be to the backward transfer to the port 4, depending on what is the need or where it has to be dropped. Accordingly it is going to depend on the parameters of those ring resonator structures actually. So how we have tried to design those ring resonator structures, that is what we are trying to see it from here now. That's what you can see it from here, that we are having now to the channel drop filter. This is what we try to design, because mostly for optical, for telecommunication applications, this is a very common device which we talk about now, where as a source we have the different wavelength of materials, like we have f1, f2 and f3, and particular frequency, or you can see wavelength, whatever the terms are okay for you. So particular wavelength of light, you can see with the f3, with the red one, is going to resonate with this, this is going to couple from waveguide to the resonator, and from resonator again to the waveguide structure. Now since if it is an optical fiber, the losses will be high. Since it is made up of on a system on chip using the photonic crystal structure, there is no issue of the coupling losses are actually very low in comparison to the optical fibers actually. So when you look at for f3, it's going to be either coupled to the port 3 or it's going to be coupled to the port 4, and either can be forward drop or can be backward drop at the drop waveguide, and at the above with the bus waveguide, those f1 and f2 are going to be unaffected. This is what we mostly use for our optical communications, where particular wavelength of light has to be dropped and the remainings are going to be unaffected. And this is what we try to design an optical channel draw filter using the circular ring resonator structure. Because when it comes to the design side, as I told you again, when it comes to the design side, it looks very like hey, it looks like you just remove the rods from here, you remove this backward drops here, you just shifted those some like rods from here to here. No, it's completely physics, and sometimes even to the mathematics. You have to calculate those coordinates of those rods position, because when you move it by your hands randomly, even though your mouse moves here there, it can be placed anywhere. That may not give you a good coupling as well, as the losses may be very high. So to get an accurate value of this coordinate axis, you have to do a mathematical, you have to apply those the triangle lattice laws, and then you have to see what is an actual coordinate of my rods. So you can apply those rules of mathematics, and then you can find the scatter rods which you're going to place, because the placing those scatter rods can improve your dropping efficiency. This is what we realized during after my master's. I tried to understand about the structures, and we tried to improve the dropping efficiency, because I saw not much of literature review on this. People are talking about a lot of photonic structure, filters and all, but people didn't use much of the scatter rods, and that's what we tried to incorporate in those designs to improve the dropping efficiency. And this is what we designed during this, and we had this publication with Optical Engineering, one of the SCI journal which we had. So this is what we can see, because on a left side structure you see them as dots actually, but they're not actually the dots. Actually they are vertically polarized rods on a wafer. And then you see again to the refractive index view, you can see that these all are the different rods, and wherever the rods have been removed, the defects have been created. This is how we can see the structure actually looks like. And the below structure, the GFT view, just shows you that how those electromagnetic waves have traveled with those resonators actually. So once we have designed this structure, so what you can see, only particular wavelength of light is going to get dropped, the remaining are going to get unaffected through those waveguide structure. And if you want to see more details, you can get down these details of the paper, and you can still get more details about it. And I will also emphasize one before I continue to the next design. You can see each of my paper, it's not just about like single author, we also have a lot of papers, but most of the work which I had is all about to the collaborative. And this is where it really helped us, not only from India, because I've been from Rajasthan, India, and then during my PhD I was in Andhra Pradesh, Vijayawada, right? But still during that time also we had a lot of collaboration from the different universities around the world, and the people who are really interested. So try to have that kind of research collaborations, guys. And that's what I always emphasize. It's not about research collaboration, it's about just a talk. After this also, how we can involve together, right? Through maybe research paper sharing, whatever the ways we can help each other. Let's try to do in that way, so that if someone is getting stuck somewhere, at least with the collaborative way, we can work together. You can see some of my authors also, not only electronics engineering, some are physicists. Like you can see Professor Bhuvneshwar Sutar is completely physicist. He's from Bikaner, Rajasthan. We have Professor Robinson, who is from Chennai, one of the Mount Zion College from Chennai. Then we have Masoud Ridwani, he's from Tunisia. So it's not about we had one author, we had the different variety of people, because you cannot do it alone, all about together. You can do it, but it will take a lot of time. So let's collaborate and work together. When you see the next design which we had on this paper, which we're talking about, the optical demultiplexer, which we designed for the 4 different channels. You can see now the channel 1, channel 2, channel 3, and channel 4. So what we try to understand now, if we change the shape of the resonator, and we can try to have the different wavelengths can be dropped at the different ports. So why can't we have the demultiplexer? And this is what we try to design, a demultiplexer. You can see particular waveguide from input side, the signal goes and output comes from here. Particular wavelength of light is going to resonate from here, second from here, third from here, and fourth from here, and which is not going to get affected, it's going to just pass through it from here. So this is how we had this wonderful work, again with a different collaboration. Even very popular we have, or also we had Professor Vijay Janyani, very popular name in terms of photonic crystal from MNIT in Jaipur. So this is what I believe we shall try to have a collaboration, and this is what I believe to attend a lot many conferences which happens as a faculty member. Try to attend those FDPs, and also to the conferences which happen on photonics and more on electronics, especially for IEEE photonics. Try to attend those events so that you can have a lot of good connection with those people actually, and this will really help me a lot, and I believe it will help you out as well, as guys. And next we designed, which we had on optical switch. Now this optical switch which we had using ring resonator structure, what we can see for the particular wavelength of light, it is going to get dropped to the port A, and then it is going to be dropped from port C to the port A. So depending on what is going to be, wavelength is going to be switched from which port to the which port with the change of temperature. This is what we realized as a design analysis of a thermo-optic switch based on photonic crystal ring resonator structure. This is we had in optic, again an SCI journal of International Journal of Light and Electron Optics. So why I'm showing this out? Because this is something which we have tried. Now this is something what you can see as an electronics teachers, which teach mostly to the digital electronics. Now we talk about the different types of logic gates. This is what you can see, a working of an AND logic gate operation, where you can see the output is high when both the inputs are high, right? And output is will be low if any of this input is high actually. And this is what we already know very well about the logic gates for the AND logic gates. Now we can also design using the OR logic gate, where the output is high if any of the input is high, either is 1 0 0 1 or 1 1, the output is high. Now we try to see the similarity between the both the designs. Now what you can see from here, here the curve structure is different, which has been especially designed to work for an AND gate operation. This structure has been especially designed for an OR gate operation. And take my words, if you try to search on internet as well, you'll find a photonics of very different logic gates. Each one is going to come with a different design. They get some results and they publish the work. That is very okay. No issues in that. But this is what we come with on our titled paper. You can see what I especially did for even for my PhD work as well. We try to design how come a single design of logic gate can perform multiple logic gate operations. Now, if I ask such a way that we, for our digital electronics, we have now to your maybe 74LS02 for AND gate, 08 for the NOT gate, 32 for an OR gate, 86 for an XOR gate. We have the different ICs to perform the different logic gate operations. But if I ask you now, can we have a single design or single IC which can perform multiple logic gate operations? And this is what we try to design with this work, realization of all optical logic gates using a single design of 2D photonic crystal bandgap structure using the square lattice structure. So this is something we come up with a solution, and this is what we had published with our optical engineering. So that's what I always say, that when it comes to the collaborations, it plays very important role, because sometimes your supervisor or the main supervisor may not help you out, but again you have a co-supervisors and sometimes you have a colleagues which can really help you out for designing those different structures actually. When you look at further, now we also have designed this, which we called as the photonic based optical encoder. Now this is what we designed on optical encoder, which is we call as a 4 to 2 optical encoder, which we can see at the 010010 input. We tried to head around 11.57 TBps, and this is what we have the improved data rates so far, which work was already published during up to 2022 actually. And this is also being published using the Photonic Network Communication Journal. So I'm not saying about what people have done. Try to see that what people have done. Try to see those papers. Try to simulate with those designs, which you already have the simulation tools, which I'm going to discuss in the next few slides. That what tools you can use to design those structures, even though it's free also and paid also. You can have any of those tools which is available in your capacity or in your institution or the organization, but try to work on them. Do not stop yourself while working on them actually. So what technology we are trying to design? We are using both for, as per ITUT, for G694.2, we have this CWDM and DWDM wavelengths for wavelength division multiplexing, and that's what we are trying to design those. For CWDM, we have around 18 wavelengths with 20 nanometer spacing from 1271 to 1611 nanometer, and then from DWDM we have hundreds of wavelengths with a few 0.8 nanometer spacing actually. So, but even though we designed for both, even for our demultiplexer was based on actually DWDM, and remaining are based on for CWDM. So what actually the spectrum we have, actually we have this O band, ordinary band, then extraordinary band, then we have S band, then we have a C band, and then we do have a large band, that's a L band. So we have the different bands for optical windows as per the ITOT G694.2. So what wavelength you want to design, it should be the one which is going to be have practical application. I can see some papers now people talking about I've designed for 1562 nanometer. Very okay, but where are you going to use it? So we need to be very particular because I told you these structures are frequency selective. So what wavelength of light is going to propagate through these structures, it should be accountable. So it's not just about you can say that we have designed may not work, or I've just took a random parameter design something, it's okay, but what is the need of it? How someone is going to take this as a reference to your work, or how someone can fabricate the structures has to be an accountability. So this is what we can see now to those photonic integrated circuits. We still have some, still we have dependence on those optical carriers and then electronic circuitry. This is what we can, still we have this electrical connections between the optics and to the EIC and then to the PICs actually. The signals are transported in the optical domains by fiber that support the high bandwidth and the low losses, that is very okay. But meanwhile, this electronic devices distributed along the backbone provide the rest essential functions needed for modern packet switching network such as routing, storing and queuing of the data traffic, and this is what we're looking forward for a further solution. And to satisfy this increasing bandwidth requirements of the emerging application and to eliminate this bottleneck, we wish to replace this electronic circuitry with analogous optical system that provides transparency and high bandwidth while consuming the significantly less energy. And this is what we're talking about the low energy or the net zero power consumption cycle. And this, the Photonics technology offers a handy alternative technology that allow us to design nanoscale circuits that can control the flow of light with innovative silicon devices. So we can use all those different types of materials to design those photonics technologies actually. And that's what we are looking forward for actually. So this is what one of the application which we designed during my PhD as well. This is where we talked about to the photonic, the wavelength division multiplexing, add drop multiplexer, integrated circuitry, which we call as the photonic nodes. And now some of my colleagues who are already working on must be talking about the electrical node for wavelength division multiplexing. That's what we can see. It consumes a lot of space, then to the lot of power as well as the very high cost. But what could be the solution, which is now we're talking about to the photonic integrated WDM ADM circuitry, which is a replacement of this analogous to this electrical node for WDM, which is which is containing actually the photonic crystal switch, which we also designed, photonic crystal based channel low filter, which we also designed, and also to the optical waveguides, which also we have designed. So yes, it could be a replacement of this electrically circuits, which is having a solution of space saving, power saving, and then to the low cost actually. And this is what the theme of this FDP says about the future technologies, which is going to bring changes through the research and innovations through those faculty members attending this FDP programs actually. So because this is what we are talking about, the need of the today's time, that how we can talk about those to the photonic integrated circuitries. So this is what we're talking about to the solutions, and this is where a wonderful slide that where we are heading towards actually, because when we say as per the theme, right, that's why I always thank to Professor Brijesh for choosing that theme for the FDP, the future perspective, because very important to understand that what is going to be happen, because we are the lecturers, the teachers, or we may be the PhD supervisors as well, right? Here I'm supervising now to the 5 PhD scholars actually, the way you must be doing in India as well. So what, you know, sometimes I feel like a professor is like, this is what I did before 20 years in my PhD, the same way they are going to still guide. But today's scholars are not only talking about those what you did 10 years before, not even 5 years before. They are talking about today, applying those machine learning models and AI models to, or data science models and machine learning models to, you know, to reframe their data, to play with them and to get something innovative solutions at least, right? So we also as a lecturer also have to be upgrade our knowledge as well as, you know, research domain as well. And that's what we can see now. This is all about the photonic electronic, the core packaging for the future generations. This is what you can see now. We have on the PCB, we have an electrical connection between those EICs. That is what we have, electronic integrated circuits, and then to the photonic integrated circuits, how they can have an electrical connection. And then the near future, which we are going ahead, is for the optical connections among them between the EIC and then to the PIC. So the data transfer rates can be very fast. And then the far future is going to be about the heterogeneous optical connection. The entire is going to be only about opticals, photonics, replacement of entirely electron. And that's what I believe the future is going to be, because someone who's talking about now to the quantum photonics, someone talking about the quantum computing, the photonics is going to play a very important role for those circuitries to be designed actually. So this is what I can show you here now. One of the recent applications I found this year, I came across this, that the ST Microelectronics launched their data centers for photonic chips developed with the Amazon, and during you can see that they have already deployed it actually, because today they're talking about the for the advancement to the AI based computing for AI processing. The data center also need to be high speed computing. So this is the way you can understand that this is where somewhere you can see how, because just talking about the research and as academia, we can talk about we have PICs, but how it is going to be implemented. Has someone already implemented those photonic chips? This is what you can see as a real-time example that how it has been already deployed actually, right? So with this we can now talk about some more other the applications or the silicon photonic products which is being deployed by, or which is being researched by so many companies. As I told you initially the slide about the silicon photonic perspective, in 2006 the Couture brought the first the photonics technology product. Then 2009 2010 Lexter brought, and after that you can see a lot many companies, very some popular names. I hope this FDP is happening in Bangalore. I hope most of the offices we have Bangalore. That's what I'm thankful to Professor Brijesh again to bringing this idea even to the Bangalore. Definitely we have a lot many companies now. We have Cisco there, ST is there, Intel is there, IBM is there. So very many companies are coming now in the India as well. Now they are manufacturing those photonic integrated circuits as well now, and this is where the future is going to be way ahead, or the far future is there for the PICs actually. And this is where we talk about now. We as a faculty and colleagues, like suppose you says Mayur or Dr. Mayur, I'm also a photonic researcher. I also want to implement, I want to do something, contribute myself for the photonic integrated circuit, but where should I start? This is very challenging. So when you look at for this slide now, it's going to give you from designing now. We want to design the fabless chips. You can go with the AMD, Qualcomm. We all have in Bangalore, all of them mostly. Marvell, Broadcom, Nvidia, MediaTek. Even you'll be surprised. This year we had IEEE Photo Society, a distinguished lecturer from Nvidia, and he is the principal investigator. He was here in Uganda as well with us. I'll show you one of the next slide. But yes, we had those design. So you see, what do you or where do you want to contribute? You want to be part of designing team. Then you must be asking which simulation tools I shall use to innovate my research or for my future research. What kind of tools I can use? So you can use maybe either the Synopsys tool. Then you can have from Siemens, ANSYS, ARM, Cadence, OptiWave, then MDP. Then we have so many other tools which can be used to design those photonic structures. And the non-chip firms, you can see a lot many firms are there which are using them. Also, we can see the equipment which is being supplied by the different organizations. Also, the different foundries who are doing in the mass production. Also, to the testing, packaging, and for assembly purpose, we have the different types of organization. Even Agilent is very common in India as well now. Integrated devices for manufacturers, we have analog devices, Texas Instruments, Micron, Intel, Samsung, Infineon. So like this, you can see wide variety of organizations which are involved in now to the photonic integration, because they are completely involved from semiconductor of those electronics now to the photonics integrated circuits. When you look at for certain analysis on that, that how it is market is being predicted actually, that's what you can see like in the last the 4 or 5 years actually, when you can see from here now that a lot many companies have come that we have already seen. But what are the major domains where people are doing research? So they're talking about now to the data center transceivers, long haul transceiver, optical interconnects, automotive lidar system, immunoassay test mostly for optical sensors, then fiber optic gyroscope for your mobile phone's screen to rotate, and then to the 5G transceiver. So it has a wide variety of application. And when you look at for their market share, from 2019 to 2025, it has grown from 117 million, you can say, around from all those domains now to around 364 million, and then in total around 480 million in the 2019 has grown now to around 3.9 billion US dollar in 2025, and it has a wide variety of applications. So now we are all experiencing 5G, but we may not be aware about that they may be having the photonics part in that research actually. So how we can do an academia and industry collaboration all together so that we can also contribute to those domains as well. And this is what we can see the latest I just came across about research by the Fortune Business Insights talking about the photonic integrated circuit market, and you can surprised to see that how this market is so big from 6 point, just now we talked about this to the this is what we just talked about to the 3.9 billion 2025. By 2026 around we may have around 17 billion, and then next 5 to 6 year time it is going to be around 65.69 billion US dollar market. So the market is big, and that's what you can see most of them in Europe. Are they talking about the VLC? A lot many companies are there in the European now to the manufacturing of those, the PICs, the photonic integrated circuits are mostly involved for the silicon photonics, because by application it's not only about electronics and communication engineering. They are there for telecommunication, they are there for data centers, quantum computing, biomedical, even for aerospace, defense, agriculture. So it just has a wide variety of applications. And when you look at for the different components, it has a mux, demux, optical modulators, detectors, optical amplifiers, attenuators, and then to the modulators. So it has a wide variety of applications. That's what you can see. And this integration can be a monolithic or it can be on hybrid mode as well, depending on what kind of integrated circuit you are developing. So this is what we can see now. The drivers, they are there for the telecommunication data centers. That is okay, but the trend which is going on is for the AI with photonic integrated circuit, and this is what is the today's time, the demand which is growing in the day by day. You'll be able to see in the next 5 to 7 years of time, we have a huge market for AI and talking about to those of PICs actually, and that's what you can see now. The next market is not only about like Europe and America, is going to be also to the Middle East and Africa as well as for Asia. There are many companies coming out to develop those of the silicon photonics actually. But we as at ISBET University, how come we are also evolved in this research actually? And that's what I'm just showing you a few more slides. I hope I have some time now, and this is where you can find the UNESCO declared this International Day of Light actually during 2015, and then 2018 2019 they had huge celebration of around the world, around the globe actually, the integrated circuits, because 16th of May declared as a International Day of Light actually. And 2019 I attended this as the ICTP Tri-State Italy, and from there I got a motivation that let's celebrate this International Day of Light through IEEE Photonic Society and SPI and OSA. Let's celebrate it every year, and that's what we tried to see. Even during 2020, we were packed inside the house, but still we were inside the house, and we were still the COVID lockdown, and so you can see the COVID virus is looking us from outside, but we were inside, and we tried to have this one of those online webinar based on the photonics for sensing and communication. This is what we did during 2020. We tried to celebrate. The same year, we also did an online again day for 21st of October as your day of photonics actually. Right there, we had the Director General, the Carlos Lee, the European Photonic Industry Consortium General was there, and this is what we had it from Belgium. Tried talking about again to the photonics research in the Europe. Then the next year we also did it. Still it was a COVID, and we were still stronger than what we were able to think. And we tried to had another webinar actually. and where we had a wide variety of people from IEEE Photonic Society, not only from US to the South Africa, Italy, Professor Lorenzo Pavesi, John Dutte from France, Professor Dabia from UK, and yes, even I was there. So we tried to have all those international leaders to talk about photonics in Uganda as well as to the East Africa, that how we can explore those opportunities. Also, we tried to see in 21st of October 2021, we also had that wide variety of, I hope you will be able to see Dr. Joe Sposo, the current the CTO for the Optica, right? Or OSA or yeah, Optica we talk about now actually. So yes, this is where I'm talking about. And any of my colleague from India right now working on computational photonics to design those tools, yes, we can reach out to Dr. Salah Obaya. He's a professor at Zevel City in Egypt. He's a very known person. He's also one of the IEEE distinguished lecturer, which has been there in the previously, and you can reach out to him for more research collaborations as well. Actually. And as I said again, 2022, we all were the corona survivors, and we were trying to head our first event as the physical workshop on about that how we can have optical fiber technology to do the fiber works on cutting, splicing, and all those things which we did using OTDR and all, which we did physically at the campus actually. And you'll be surprised that this work which we did, this workshop was also published with the IEEE Photonic Society in their newsroom, that how we did something in East Africa as well. And the same year we also did a day of photonics, because sometimes when it says about photonics, it's not just only about optical fiber communications or to the data transceiver. The light, the photons, or the photonics is also part of the light which is falling on your camera to click the picture. So what is the beauty of those cameras? We tried to have one of the very very fashion designer photographer from Italy, Mr. Morpheus. He tried to explore that how the camera lenses, not just about you have a camera and you just click a picture. No, there's a beauty of light, that how we can make very beautiful pictures. That's what we did in the this year. And we also had to get a chance to celebrate the Universal Acceptance Day along with the International Society of Uganda chapter. That's what I believe. Even ICANN and Universal Acceptance try to collaborate, and let's work all together actually. And this is what we did in 2023. This is what we had, the UNESCO International Day of Light, and you'll be surprised that here we had a Dr. Dominic. He's the Assistant Secretary General for UNETCOM, Uganda National Commission to UNESCO. And you'll be surprised that he also added me later on to the Natural Sciences Committee of UNETCOM to UNESCO actually in Uganda. So this is what we had, the different speakers from academia and industry and even from the government, and let's all try to work together with the different types of associated with the industry partners actually. And also that year we also tried to celebrate IEEE HDB symposium. We also had our that time the chair, the global chair for IEEE HDB, Professor Lavanga Hubbard was there with us. So yes, this is what I'm trying to show, that how we also did as a collaborative activities, and that's what we all as a faculty members can do, because we cannot travel every time to all the events. So let's collaborate and work together. That is what we believe so. And this is what we did just last year. We also tried to did the ideal, which we are celebrating from past consecutive 6 years now. And here we did for software developers, because here people are talking about, okay, you're using a simulation tool is okay, but can you talk about computational photonics? How we can design our own software to work on those photonic structures? This is what we did about the enhance your software's global compatibility, that for developers in Uganda, that how they can develop certain softwares actually. And we had a lot of Integrated Society partners here, and this is what we celebrated. And just last year, this year actually, we also celebrated International Day of Light along with the International Year of the Quantum Science and Technology, also to celebrate the 60th anniversary of IEEE Photonic Society. And this is what we had people from government, academia, and industry tried to celebrate that both the days, which is by UNESCO. And to celebrate more in special to the 60th anniversary of this year of IEEE Photonic Society, we celebrated along with the this is what called as a distinguished lecture program, where we had Professor Daniel Amkuster. He's a principal hardware system for NVIDIA in US, and he was here with us just last month, and it was a wonderful session actually. So what I'm trying to show, not to just show that what events we are doing, we have to make it continuity. Secondly, we have to have a lot of collaboration from academia and industry all together to make it as a grand success. And lastly, before to show you that 2023, I was nominated for the most innovative people for Photonics, and that's what I have been. I was there among 100 people around the world, and you'll be able to surprise again to see on the entire map. There are many people from the Europe and America and all, but you'll be see that in the entire Africa continent, there was only one person who was nominated actually, and that's what me actually. So thank you so much again for your kind support and all. That's what you can see. One person was from Uganda, rest are from the different part of the countries actually. Lastly, I can say that this photonics technology allow us to manipulate the light in a ways that have not been possible before actually. So this is where is my last slide, and this is all about my beautiful Kampala city where I stay. Thank you so much, Professor Brijesh, and the team, even to the director for organizing this kind of FDP, so that the faculty members, especially because they are in academia, right? And the today's term academia is not same as before 5 years, because today everyone is talking about machine learning models. So either you're doing electrons and communication, either you're doing telecommunication, or you're doing electrical engineering, but everyone is trying to see that how machine learning or AI can be incorporated over there. Right. So we as a faculty also try to enhance our knowledge, and I think photonics is one of the domain which some of the faculty will take some interest. And if you have any questions, you can reach out to me through email, and then maybe we shall discuss a way forward for it. So with this, thank you so much once again. I'm keeping some time for a Q&A session so that we can further discuss in case you have any queries here. With this, thank you so much, Professor Bridges and the team. Over to you. Thank you so much once again, all of you. Thank you once again.
Yes, sir. Yeah, am I audible? Hello? Am I
Hello.
audible?
Yes.
Yeah. So I guess we don't have any question since nobody has asked any question till now. So I think we can conclude the session now. So before that, so I sincerely thank Dr. Mayur Kumar Chippa for his insightful and engaging talk on towards the future photonic chips, bridging the gap between photonic and electronics. Your expertise and valuable insight have greatly enriched the FDP session. I also thank the organizing committee of CMR University and all participants for their support and active engagement. With this, I formally conclude the Day 3 Session 6 of 5 Days International FDP on Next Generation Technologies and Research Practices for Academic Excellence. Thank you all and have a pleasant evening. Thank you, sir. Thank you so much. Thank you so much for your time.